Denis Belomestny, I'm sorry for the pronunciation, who's going to speak, who's from Duisburg, Essen University, and he's going to speak on kernel forward reverse regression for the Schrodinger Bridge Problem. Thank you very much for coming, and please take it away. Thanks.
Thank you very much. First, I would like to thank the organizers, Raoul and Christian, for inviting me. This is a very nice place. I'm a second time here, so it's always a pleasure to be here. So I will talk today about the Schrodinger Bridge Problem. This is a kind of classical problem in optimal transport. Recently, somehow we see the revival of interest to this problem because of application, new type of application, generative modeling. So this is the essential of the Schrodinger problem is how to construct the main question, how to construct a Markov process, more precisely, or in particular, diffusion process, which somehow starts from a given distribution and gives at the end a time capital T another distribution. So somehow the endpoint distribution are fixed, and the main problem is how to construct the process which somehow has this kind of bridge property, but additionally it also should satisfy some optimality in the sense that the Kullback-Leibler divergence between the on the path space should be also minimized somehow. I mean, it means also that the cost is measured basically in terms of entropy of Kullback-Leibler divergence, and this cost should be minimized. And okay, this is of course, I would say, a classical problem which goes back to Schrodinger in 1942, but still there are some open, I would say, problems, some challenges, mainly on computational side, and therefore I also like to draw your attention of math computing community to this problem, because I think there are many issues here are not well resolved from the point of view of numerics also. Okay, so I will not go much into details about the Schrodinger problem. What I only say is I would like to give this main result on Schrodinger problem, which says that the optimal coupling should be of this form. So this is coupling between the endpoint distributions. And this optimal coupling should be of this product form, where Q is a transitional kernel of the base process, so to say, of the base Markov process. Or you can think as any kind of transitional kernel of any process. Later, I will somehow specialize it to the case of diffusion process. So Q will be transition kernel of the Markov process, of the diffusion process. And nu naught and nu t are the so-called Schrodinger potential, which are to be found. And additionally, we of course have this constraint that the marginal distribution, so the first marginal and the second marginal are given. And under these constraints, we need to find this Schrodinger potential. And this is kind of the main numerical problem here. Of course, here we can assume, usually it is assumed that the Q is known in some sense, the transition density of the underlying base Markov process, or at least we can generate samples from it. And this, in the case of diffusion process, is a reasonable assumption that we can generate from it, because usually we don't know Q analytically in the form for general diffusion process. So this is a kind of core result in this Schrodinger problem, the so-called Schrodinger system. And this is a Schrodinger system is exactly what I say. This is this derived from this representation. And here there's additional constraints on the marginals somehow presented, taken into account, and this is a, you see, this is a highly nonlinear system of equation for potential, because if you look more carefully at this equation, what you have here nu, you have here nu t. So it is a kind of, I would say, quadratic type of nonlinear integral equation, and you need to solve it. Imagine, so you have Q kernel, and you need to solve this type of equation. And the general approach is how to do this. But if we go somehow, if we look at this problem as a problem in numerical mathematics, as a problem of solving some nonlinear integral equation, then we can think that here you can use also several methods, various methods to compute these integrals using Monte Carlo. Because if you say, consider more general diffusion process where you don't know Q analytically, but at least you can, what you can do, you can compute these integrals using Monte Carlo, and then you can combine this Monte Carlo with fixed point approach with Picard iteration to solve this system of integral equations. And now, if you recall that, for example, it's also clear relation to the multi-level method, because the first introduction of the multi-level method by Heinrich was exactly done for solving integral equations. Yes, so if you go back to the history, kind of integral equation was kind of first type of equation. I remember the first paper of Heinrich and Peter Mate from Weierstrass Institute. At the time it was about solving this type of integral equation. It was the first appearance also of this multi-level approach. And okay, so basically you see here, you can try to do this here. What I present today, I will not touch multi-level, but I will rather go to the methodology from statistics, or to say also machine learning. I will approximate these integrals also using in non-parametric way, using kernel regression combined with Monte Carlo. So basically, maybe first I will also give some details on the connection between Schrodinger problem and generative modeling, and also to the so-called dupe H transform. Because, okay, Schrodinger problem and this formulation, which I presented before, is a static formulation, because you have here, basically time here plays no role. You only have fixed 0 and fixed capital T. But more interesting, of course, for generative modeling in machine learning is a not static but dynamic formulation, where you can construct process, the diffusion process, which starts at the distribution rho naught and ends at the distribution rho capital T. And this is related to the two notions, reciprocal processes and the notion of dupe H transform. So what is a reciprocal process? Reciprocal process is a kind of generalization of the Markov process, where you somehow condition not only on the, so to say, the point, you condition on 2 points, initial and the final, yes, basically. And then you have this Markov process, sorry. I mean, here the formal construction, how you can construct reciprocal process in continuous in time. But basically, the main property of the reciprocal process, okay, for example, here you can compute expectation of any function g of x naught xt mu, where mu indicates that there is a kind of coupling behind this, coupling between, and this is the expectation of this. You see here, mu is a coupling between initial and final state, but then you can construct this process on the whole, on the interval 0 capital T by considering some time discretization and so on. And basically, you can construct this continuous process, Markov process, which has this nice property. This is the kind of characterizing property of the reciprocal process. If you see For Markov process, it would be like for standard Markov, you don't have xt here, but only xs, yes? And this is the reciprocal process. The Schrodinger bridge is a special case of this reciprocal process. This is a Markov process, which is also reciprocal. And is exactly this gives us this form of the coupling. This coupling, this multiplicative form, this product form of the coupling. This also, of course, can be derived directly from the Schrodinger bridge formulation by using Lagrange multiplier method applied to this optimization of the path space, this optimization problem of Kullback-Leibler. You can also derive this, but you also can derive this from general Markov reciprocal processes. And now the second important ingredient, this is a dupe H transform. This is about how to construct diffusion process, which starts at the given distribution and comes to the another distribution, which is also fixed at time capital T. This can be done by using this dupe H transform, which basically boils down to changing the drift of the diffusion, which is very popular tool nowadays in diffusion models, in generative modeling. But here is for Schrodinger problem is a bit more complicated, because in standard diffusion setting, which is quite popular nowadays in machine learning, your idea of changing drift is based on ergodic properties of the underlying process. So you know that if time grows for large time t, you go to the normal distribution or kind of some invariant distribution. Here, capital T is fixed in a sense. And but construction is very simple. So you construct this, you change the drift using this H function. And this H function, so it's exactly this dupe H transform. If you basically compute the transition density of the new process and relate it to the transition density of the underlying process, it will be exactly the dupe H transform. And here, the main issue is, of course, how to construct this change of the drift, how to construct this function H star. And it turns out that this function H star is directly related to the potential nu T, the Schrodinger potential. But of course, this potential is not known. You need to solve the Schrodinger system first, and then you can plug in this estimate here, and then construct function H, and then run the diffusion process. But you need, of course, somehow to know this H at many points, yes, because you run your diffusion and you need to compute H at all on the whole trajectory. So basically, this is a motivation to estimate H somehow non-parametrically, the function of X, and also function of T also as well. So basically, this is a kind of idea. So first, in order to apply this idea to generative modeling, say to the problem, say if you know, for example, in generative modeling, usually you know the final distribution in the form of sample. So you have a sample from the distribution, say rho t, and then you can estimate this integral here. Basically, I mean integral, not this integral, but integral in the Schrodinger system using kind of this empirical measure. But okay, now I will concentrate on the problem how to solve Schrodinger system. There are several quite efficient methods to do this, and the most famous one, this proportional fitting. This is called also Sinkhorn, based on Sinkhorn algorithm. This idea is, if you translate it somehow to the language of numerical mathematics, this is simply Picard iteration, yes, or fixed point iteration to solve this nonlinear system of equations, yes. Yeah, of course. I need to do. I will explain it. This problem is not easy at all here in this particular case, because this fixed point problem, the underlying fixed point problem, is not that easy. And I will show the main difficulties. Maybe I will skip this. Yes, one important remark. So you can translate this Schrodinger system. You can write it down in another way, in a way of expectation. So you can introduce forward and backward process. So forward in time and backward, because if I can write it in this way, because if you remember, maybe I can go back a bit. So it was kind of two equations, yes? So you see one, I mean two integrals, one respect to x here and one respect to z. And this is the kind you can think this is backward because you integrate with respect to initial. And the second is forward because you integrate with respect to z. And this you can represent as an expectation for two type of processes, backward and forward. It is exactly what is written here. And basically, you can see here also already that this problem is related to the problem of nested expectation. Because if you say express one potential and plug into another equation, you get a nested expectation problem. This is exactly this connection to nested expectation, which is also can be solved using multi-level Monte Carlo. So maybe this is a short recap of this backward process. So basically, in order to compute this integral, or expectation, which is here backward, you don't need to somehow to run the whole reciprocal process. You only need to compute expectation perfectly. And for this, it is enough to consider the so-called slight version, or I would say simplified version of this backward process, which is also well known, where the change of the measure change of coefficient is much more simpler than in the reciprocal process. You don't need really to change the drift in a complicated way, but this is kind of reverse process, which is well known. So Christian worked with John on this. This is many papers. But what I only mean here is that in order to compute such expectations with respect to this, say if you integrate with respect to initial, with respect to W here, you don't need to run this complicated reciprocal process, but you can consider this simplified version, and it will be also, if you weight it with this y, calligraphic y, it will be perfectly fitted. So basically, this is kind of simple remark on how to compute the second integral, because the first integral is a forward process. It's very simple. So, okay, how the algorithm could look like? So you can simply run two type of process, forward, reverse, and then you can use kind of a kernel regression to compute these integrals involved in the Schrodinger system in a non-parametric way. Like you compute simply, this is a kind of kernel regression on the paths, on the forward path and reverse path. The idea is very simple. You can do this, and then you can compute this potential iteratively, and kind of following this Picard iteration idea. And you can do this. But the main problem is, of course, if you now go to the analysis of this problem, you will immediately see some fundamental difficulties. And now, before I go, first I would like to highlight this difficulty and somehow the difficulty of the underlying fixed point problem. Because, okay, now you can simply you can formulate this as a one single fixed point problem if you replace one potential, express one potential from first equation and plug in second, then you get the following one fixed point problem with respect to function g. So here you have already, you see here you have expectation here, expectation outside, so it already has a form of nested expectation here. Yeah. This is one possible formulation, but you see here, one expectation is outside expectation and one expectation inside. So you have two expectations and one inside, you integrate with respect to x. You also have here x. So you have one inside, so it's a real typical nested expectation problem. And here you need to, but it's kind of, what can you do? This is not only expectations, this is also, you have an integral equation, fixed point equation with respect to g. And also what you immediately can see here, this expectation somehow doesn't have unique solution because you can multiply function g with some constant and you see the solution will be and then divide and you will get the same solution. So basically this is a problem that somehow you need to consider a class of solutions, equivalence class with respect to this all possible multiplication with constant. And this is not completely easy. And therefore, people who studied it, they introduced a special metric, the so-called Hilbert metric. And this Hilbert metric is very useful here because it exactly consider solutions, consider this class of equivalence. Yes, I don't know, maybe many of you know what is a Hilbert metric. I just introduce it shortly. This is a kind of logarithm of this maximum. You can think maximum divided by the minimum of the ratio function. So this is a kind of, I will not go into details much because I don't have time for this, but this is metric is somehow well known and has somehow this in particular suitable for solving these problems where not only this problem, but also linear equation problem, fixed point for linear equation, where you have some, yes, as you have this multiplication with constant should lead to the same solution. And now you can consider some modified iterations of this equation. So this is, you consider basically fixed point iteration, Picard iteration, but you also make some scaling because you somehow scale by this second norm, the two norm of this function. Then you start somehow and you go, sorry, here should be not f naught, but g naught. So you start at some point g naughts and you iterate. And ideally, if all these integrals are known perfectly, you have this contraction property. But this contraction property, quite important, holds only for this Hilbert metric, not for standard metric. Any standard metric will fail here. But somehow you can, of course, transform this result also to more standard metric like uniform or L2 if you introduce some additional assumptions, some normalization on the Schrodinger potential. Okay, this is the underlying fixed point problem. I subdivided it here into several problems. So you basically, you can represent this operator C as a kind of application of several operators. This one operator is this 1 over f operator inversion. And the second operator, second two is this two linear integral operators, which are basically expectations, yes. And if you represent the operator C in this form, it's clear how to proceed and how to analyze. You need to analyze each of these operator, and you can also immediately see that this D operator is somehow, this is invariant with respect to Hilbert metric. Yes, and this is important. This is also a reason why people use here Hilbert metric, but this 1 over f operator is invariant. And okay, this is a kind of idea now. Yes, what's about convergence? As I said, if all integrals, all expectations are known perfectly, then okay, you have this contraction. Otherwise, you don't have this. And also, at the end of the day, we would like to get some reasonable results for more natural metric or more natural, somehow more usual metric like uniform metric. And therefore, we introduce some additional assumption on potential. In particular, what we assume here, okay, this assumption is kind of mild one. So any somehow on any set, which is basically a compact set, we have bounds from below, from above, for the transition density. By the way, the convergence proof, the standard convergence proof for example, this contraction proof for Hilbert, for the Schrodinger system, usually done only for compact case. The case where your rho, the marginal distributions are compactly supported. Now we have new results. Quite recently, there was a development on theoretical side. People got some convergence for the case where we have log concave distribution. But okay, so for this, for my talk, I assume kind of that I have a rho naught and rho t have a compact support. Although, from the point of view of application, this is not a reasonable assumption, and because usually you don't have such compactly supported distribution, and more somehow reasonable would be to consider, say, Gaussian or sub-Gaussian distribution or something like this. Anyway, here assumes this, some bounds, but what is the most important assumption here is this normalizing assumption for function G star. You can formulate it also in terms of potential, but also here formulated in terms of G star. And this is crucial assumption. We somehow say take one particular solution from this whole family of solutions up to multiplicative constant. I take one which has this integral, say 1. And then if I assume this, then I can already relate my Hilbert metric to more standard metric. And also I can prove kind of convergence in this case, also for the situation where we have uncertainty in the integrals, where all these expectation integrals are approximated using some numerical method. So the procedure looks like here where I compute these expectation operators or linear operators using this kernel regression, but we need to regularize it. And this is quite important. This regularization we need to cut because we may have that there is this denominator is 0, so we need to cut. This is first regularization. And by the way, here the kernel is assumed to be positive. And then we start with some distribution phi, which is a distribution for x, for forward operator. And then we also the same we can do for the backward operator. This is not so, this is more or less clear how to do this. But what is the most important here, and what we also take from us some time to understand, is this 6-point iteration. Because here you see, okay, we can compute operator E, expectation operator, we can approximate D. D is clear, you don't need to approximate it. But if you now perform this Picard iteration, this truncation turns out to be quite important, because without this truncation, you will not converge at all. And so or you can get very bad convergence rates. And this truncation is based on this bound, prior bounds for the function G, which come from this normalization. And without this truncation, you cannot get any reasonable result. This is quite important. And also here we do some normalization in order to achieve this constraint that the integral of G star is equal to 1. So we normalize each iterates. In each iterate, we normalize the estimate. And after this, again, we get this contraction. And also we get some bounds on the distance between gk and g star. Maybe I will not go much into details analysis, but only one important thing: if you like to rigorously analyze the convergence procedure, you need to take into account that here you have computed some random point at any step. You need to compute, say, difference between expectation and its approximation, but at some random point, which depends on the whole history of your iterative procedure. And this makes it a bit difficult. So for example, I apply here some results from empirical processes, from statistics, but this additional dependence on the history is not so easy to handle. And therefore, we apply here some uniform bounds from empirical process theory to get reasonable result. And what we get finally, gets this rate. This is rate in H metric. For this is n is the number of trajectories used for forward and reverse process, used to approximate the expectations in this Schrodinger problem. And then if you choose k optimally, you will get rate, the final rate of this product. And also you get rate in the infinity norm and the sup norm, because we can now relate the H norm, DH norm, the Hilbert norm, to the standard supreme norm. And this is also not completely obvious how to do this, but under this normalization constraints, we can do this. And this is kind of standard rate, more or less what it means, standard non-parametric rate in statistics. We were able to show this is optimal rate, cannot be improved in general if you have some smoothness, because we have also assumed some smoothness of our transition kernel. So we need only smoothness of transition kernel, more or less, for this. As pi initial distribution, but you can choose it. This is not, pi is not so important here, but transition density should be smooth enough. And under this smoothness assumption, we can prove this rate and also low bound, showing that this cannot be improved in general. So this is the main, so to say, main result, main convergence. And what next can be done? As far as I see, this is I already mentioned, there's a clear relation to multi-level Monte Carlo. So you can apply multi-level Monte Carlo in each step of your iteration procedure to compute this integral. You can also formulate this problem as a nested Monte Carlo and then use multi-level as it done for nested Monte Carlo is another possibility. You can try to analyze this, the cost, because I don't analyze here really cost, only about convergence rate. Of course, cost is here also can be computed, but basically it's would be quite interesting to compare cost and to compute, say, to develop math with minimal cost. And I think also this should be somehow related to the integral equation, to the problem of solving integral equation with multi-level, which was done in the early works of Heinrich. Also, yes, optimality of the rates and also kind of dependent data problem is important here. We assume that the data and at some point we have new data at each iteration, but later somehow it will be more reasonable not to assume. Okay, this is all what I wanted to say. Thank you very much.
Thank you very much, Denis, for your nice talk. Do you have any questions from the audience?
Thank you very much for this very nice talk. I mean, if you're thinking about the proof, but also the implementation, do you need to take care to guarantee that the G doesn't become zero somewhere, or is this kind of automatic?
No. This is quite important. This is exactly done by this truncation. You see this truncation from below and from above. No, without truncation, it doesn't work at all. So really, it's important, but you need to know somehow where to truncate.
Yeah.
And for this, we need some prior bounds. But it's usually also done in numerical mathematics, often that you assume something on prior, because usually here the prior bounds is like, okay, we need bounds here on, say, Q, but okay, for Q, we may have bounds, and also for rho, for marginal distributions on compact set. And also this normalization would lead to this bounds, to some bounds from exactly computable bounds, so to say, for G star mean and J star marks. And these bounds are used then in the truncation procedure here. And this is crucial, because without truncation, it will not connect.
But do you think if you implement this,
Yeah.
that this is crucial, or is it more like
I
something
think yes,
that you need for the analysis?
You need to do this, because otherwise, you know, what is the problem with it? As I said, this is the kind of why people consider this Hilbert metric, because it's somehow invariant with respect to this multiplication of constant, but you don't know this constant basically. And it may happen that the procedure, especially if you estimate the integrals, it may happen that here you have kind of big values of this Q and on G, but still, I mean, the Hilbert metric can be okay, yes, but I mean, in standard, not.
For the same reason, in the kernel.
Yeah, of course, you should play somehow with this, yes. Otherwise, you should take it, and it should be taken with care, because it's their optimal value, of course, but this does not work in practice. Usually, this is only for rates, but usually you need to play maybe some kind of adaptive choice. I don't know, but there, of course, yeah, it's very important, yes, how to choose that.
We're mentioning Monte Carlo, right?
Yeah.
I think that there could be an advantage of using another quadrature.
Yeah, of course. I mean, especially if dimension is not so high here, you can use any numerical method to compute this integral. I mean, it's quite clear. I mean, because here you have these integrals. How to approximate them? You can use quadrature. Yes, why not? If you know Q, say in some, you can use quasi Monte Carlo.
Particularly for the expectation we did recently.
Yeah, it would be quite interesting. Yeah, you can use this different type of numerical methods to compute these integrals, and then you can try to do this convergence analysis for this particular method. Because I think this is a kind of, for example, multi-level. It would be nice because you have here again.
Yes.
Yeah, it would be a kind of nested expectation. I think it's.
I understand that it is very natural to think of fixed point iterations here. Is there any way you could formulate this as a minimization problem?
Yeah, there's also
iterations are more stable than fixed point iterations. Right?
Yes, I agree, and you are completely right. There is another formulation, which is optimization. For example, you can formulate as a fitting to marginal distribution over class of these functions H. For example, here. This group H transform. Here, this class, you can parameterize, say, function H by parameterizing this potential nu t or log potential. Then you can introduce some parameterizations. You optimize over potential, which somehow lead to their best fit to the marginal distribution at the end if you start it wrong. And this would be one big optimization problem. Yes, and this would be, yeah.
Hierarchical stuff also works well.
Yeah. But it will be non-linear, rather non-linear. Okay.
Thank you.
I'll be quick. I was just gonna follow up on Raul because I had the same thought. So in optimal control deterministic problems, people are using these shooting methods, and you can do a shooting forward, back shooting, or multiple shooting.
Yeah. I don't know, but because of course you can formulate this method as a kind of, you can go to the original kind of Schrodinger problem as a, say, optimal control problem, or optimal with quadratic cost. But then it's quite important that you have quadratic cost. If you have no another cost, say quadratic cost, means that you have normal Q, Gaussian Q. If you don't have normal Q, say Q would be more general for more general diffusion process, you will not get a kind of advantage of considering this kind of optimal transport problem in the original form and using some optimization. Here, the advantage is you have the Schrodinger system is quite general. Yes, you can try to solve it. Of course, is Picard.
Like you have a time testing method that goes, like you think of it pseudo time.
But yeah. But it's I mean, yeah. But okay, for solving the system also. Yes. Okay. I guess.
First of all, thank you very much for the talk. Just so that I understand correctly, you are matching only the marginal distributions at time 0 and time 1 of the coupling, right?
Yeah.
Is there a way to match the joint distribution as well? I mean, there are some applications where this would be.
Yeah, I know. There's a time series. You have some recent results on multi-marginal Schrodinger bridge, where you have some kind of grid, time grid, and you'd like to match distribution on the time grid. Yes, these are you can modify, but then you get kind of more complicated Schrodinger system, so to say. You can also formulate this; it's become more difficult. But if you mean continuous type of, if you have a kind of flow distribution, a matching flow distribution, it is even more difficult. But in machine learning, you have many methods how to try to match the flow of distribution in a bit different way. But for diffusion process, it would be kind of more difficult. And so, but in general, my answer is yes, you can formulate this for multi-marginal problem. If you mean this, I don't know.
Pretty much, yeah. I was thinking of protein docking applications where you know the initial and final position of a particle, and you want to make sure that the joint distribution is kept.
Or you can imagine, or you can put some constraints on your coupling. Maybe you have some constraints on the path distribution. Maybe you need some additional properties of your coupling of this distribution apart from marginals. This is okay.
And another quick one, do you have the preprint ready? Is it uploaded somewhere? I would love to see the details.
What do you have?
Do you have the preprint ready?
Yeah, it's almost ready, but
Almost
will be. I can send you if you write.
That would be great. I would love to see it. Thanks.
Okay, so we're at time now. So let's thank Denis once again. Thank you so much, Denis. So we resume at 2 o'clock with the talk of Christoph Reisinger, and the chair will be Christian Bayer. Thank you.